All right. As we begin this lesson in Physical Science 20, this is the beginning of Chapter 8 in your textbook. And the title of this unit is Heat. And there's really only one chapter we're going to be looking at in the textbook, and that's Chapter 8. So before we get into these notes here, let me just talk briefly about this Physical Science 20 course. The first part of the course is primarily physics, and so we've taken a look at light and mirrors and lenses and that sort of thing just recently. And we're going to move towards chemistry as the other part of the physical science. And this is sort of the link between physics and chemistry. It's sort of the transition chapter, if you will. And we start talking about a lot of chemistry-related concepts in this chapter. So this chapter is basically it's on heat, thermal energy, kinetic molecular theory. So the notes say this. Here we go. If you're copying this down, certainly copy down all the underlined pieces or just the highlighted parts that I'm going to go through here. First of all, kinetic. Let's just take a look at kinetic molecular theory here. Kinetic means motion. So we're talking about movement of what? Molecules. And it is a theory. Okay, so it's a way of helping us understand a certain situation. So the movement of molecules or particles, atoms, that sort of thing. Thermal energy. Okay, it's similar to heat. Thermal energy is energy caused by motion of particles. So as particles vibrate and as they move around and as they bump into each other and cause sort of this friction and these collisions, creates what's measured as thermal energy. Now, if you think about the movement of particles, Brownian motion is the term used to describe the erratic natural motion of particles. And it's because of the energy that they all possess. So I have I just want to open this here for you. It's just this little thing right here. And if you look at all these particles, and it's tough to tell where each particle is going, but they are randomly bouncing around and bumping into each other, bouncing off the walls. And this yellow particle here is sort of an example of how the air might move, a particle, or how it might be a result, the motion might be a result of random kind of bumps from these other particles in the system. So these particles are all representing, random, natural, erratic Brownian motion. Scientists develop theories based on observing things and seeing how they behave under certain circumstances. So that's where the theory comes in. This is all based on observation. Problem is what happens when you're trying to develop a theory about something too small to see, like atoms or molecules, particles, such like that. Scientists use a model. They create a model or representation of the thing that they're trying to study. Okay, so a scientific model is simply a representation of something that's either too large to see at once, too small to see, or something that's really, really complicated and they're trying to simplify, trying to get a basic understanding. So if the model gives the same results as the real thing, then it's considered a good model. So again, a model helps us understand how something behaves. A scientific theory is an attempt to explain what happens in the real world. And the KMT is a good theory, and it's based on the idea that these tiny particles, whether they're atoms or molecules, are moving. And there are 5 kind of basic points of the kinetic molecular theory which I'd like to go over here right now. So, point number 1 is that all matter, point number 1, all matter is made from tiny moving particles. So if we consider solids, liquids, gases, your desk, your pencil, that sort of thing, they're all made from particles, and we call these particles atoms or molecules or some basic building blocks like that, right? And so if we consider that all matter, even stuff that we appearably invisible like air, that's made of particles as well, then this theory gives us a good basis to the theory. Okay? So point number 2 is that different substances have different particles. So the particles in your desk are different from the particles in the air. If you look at the periodic table, okay, the elements of carbon and calcium are very different. Their atoms are different. So they have different particles, different atoms, because they are different substances. Point number 3, particles are in constant motion. Okay? Remember, kinetic molecular theory, talking about motion. So that's the big deal here with this theory. And we're going to see about, we're going to see a little bit later about the difference in motion and how that exhibits itself. Okay? But everything's in motion, either not a lot of motion, okay, pretty still, just maybe vibrating in place, versus, racing around all over the place. Okay? We're going to talk about that in a minute. Number 4, generally, the more energy that something has, the faster the particles move. Increase the energy or the heat or the temperature of a system, the particles should move faster. That's what we're finding here in this theory. And number 5, the attraction between particles gets weaker the farther they are apart. So, in this theory, particles would attract each other. Certain particles attract, certain particles repel. But the closer they are, the stronger the attraction. The further they are, apart, then the attraction or the repulsion, the forces between them, are weaker. Okay, that's important. The closer they get, the forces between them get stronger. So I already mentioned here that a theory is considered a good theory if it explains the real world correctly, and the KMT seems to do that. Now, what are the implications of the kinetic molecular theory? Well, it helps us explain the states of matter really well. Solids, your desk, your chair. The reason why you're able to sit on your chair and to write on your desk is because the particles in those solids are very close together. They vibrate in place, they don't move around a lot, and they maintain shape and volume real well. Right? If your chair was liquefied, right, you wouldn't have a very good time sitting on it, right? You'd just fall right to the floor. Certainly, if your chair was in gaseous state, you couldn't really sit on it. Wouldn't support you, would it? Liquids. Okay, you know about liquids, liquid water, let's say. These particles are still close together, but not as close as solids. They still vibrate, but they move around more. They move around each other. They're pretty good at maintaining their volume, but not their shape. So they can take the shape of any container, right? If you have a flask, like this, and you have liquid in the flask, it's going to take this shape. It's not going to randomly, spill out if it's just, sitting on the desk. So it maintains the volume fairly well. It'll stay in about this volume. But if you had a different shaped container, right, the liquid would be a completely different shape. Right? So it's like this, trapezoidal maybe, or takes the shape of the container. But the kinetic molecular theory says that these particles move around a little bit more. That's why they're able to change shape and take the shape of their container. Gases, on the other hand, particles are very far apart, and they bounce around each other quite a bit. They bounce off the container, so therefore they fill any volume that they're in, and they can change shape, obviously, really easily. And in these diagrams, we have examples of solids. You see how they're all densely packed. They're not moving around very much. They're in very good order, you see. They're very still. They kind of look like soldiers standing at attention, right? Or in some kind of marching parade, right? They're very orderly. Liquid, little more chaos, right? Little bit more movement there. More energy, more movement, right? A little bit more random. And gas, of course, gas is just totally off the wall, right? Solid, liquid, gas. Gas fills the container. It wants to get out. It's moving around quite fast, and they're bouncing off each other, and they're really active, and they really want to get out of there. Solid, they're just fine to stay in their nice little rigid, situation there. Gases, high energy, lots of bounce. The kinetic molecular theory also explains changes of states real well. So if we are going from solid and you're changing state to liquid, that process is called melting. You see how this arrow is going here? Okay, from solid to liquid is called melting. And, if a solid gains energy, like, if you have a block of ice, right? Right? That's not a very good sorry, a block of ice and you heat it, right? Fire, oh, fire, heads up, the logs. And what's going to happen? Well, it's going to start to melt, right? You can have drops, and this is going to decrease in volume a little bit. It's going to start to melt and liquid, right? So solid to liquid. What's happening? These particles that are very, orderly and are fairly rigid start to move around, right? Oh, let's get out of here. And so they start to become liquid, and they start to fall off, right? Liquid going to gas, evaporation. Now, I'd like you to put boiling on there as well. Okay, and there is a difference between evaporation and boiling. Boiling represents a change from liquid to gas once the boiling point is reached. So there's enough temperature that these particles are forced out of the liquid into the gas. They have so much energy, and if you think about this liquid, right? If you've got liquid water and you heat it up, okay, there's a fire again. Ooh, it's hot, careful. Then what's going to happen? Steam, right? Well, if you hit 100 degrees Celsius, 100, then you're going to have steam coming out of here. Boom, they're forcing those molecules out of their, semi-attractive state where they're kind of okay to hang out with each other, and they've got so much energy they need to bust loose, right? That's boiling. Okay, you reach a boiling point, they change phase. Evaporation. Think about a little puddle of water on the ground. Okay, and it's a really hot day, and you go back there a few hours later, and you just have dry, cracked ground. Okay, the water has left into the atmosphere because of pressure change or because of just relative humidity or whatever. It's changed from liquid up into the gas, not necessarily because this little puddle started to boil, right? It didn't start to boil, right? It just sort of evaporated and created a dry, empty space there now. So that's evaporation, but still the change from liquid to gas, evaporation. The process of boiling, right, is an increase in temperature forcing this to happen. Evaporation is just sort of a natural, depending on other conditions. Okay. Condensation. I don't know how many of you had a shower this morning. Hopefully all of you, or at least most of you. Doesn't smell too bad in here, so I'm assuming that at least some of you did. But when you get out of the shower, right, the air is very moist from your hot shower, and usually the bathroom is quite a bit cooler than your hot shower, right? So when you step out, there's what? Fog everywhere. Yeah. There's a mist in here, right? There's gas vapor, right? And what about the mirror? The mirror is always foggy, right? Think about a foggy mirror. That is the hot gas water molecules in gas stage bumping into a cold mirror and condensing. They're all coming together now because they lose so much energy, and they don't move around so much, and they start to kind of get together. You see the fog, and then eventually drips of liquid, right? Liquid, gas. If you're going from gas to liquid, it's called condensation. Okay, plane flies through the atmosphere, way up high. Hot plane, right? Cold air. What happens when hot and cold meet? We have some condensation. Okay, so the hot air that's left behind by the airplane. Okay, right? It's my airplane. I know. Good job. Right. So you'll see kind of the formation, the condensation of air. Remember, this is really hot, and the air up high is pretty cold. So as soon as a hot machine hits the cold air, this water that's in here says, "Wow, I got to come out and kind of be a cloud. We got to get together, man. Lots of energy, bump into each other." Okay, so we're going to start to condense. All right, now the process from solid to gas. There is a situation where a solid could go directly to gas. That's called sublimation. If you think about ice cubes in the ice tray in your refrigerator, in your freezer, okay, over time those ice cubes will get smaller and smaller. You think, well, where did those go? What happened? They just get old and shrink, or what? Well, solid has gone into sort of the gas state, right? And if there's a sharp temperature change, this can go directly to gas without passing through liquid first. That sort of situation is sublimation. Okay, so that's changes of state, some really poor drawings, and hopefully a little explanation on what these words mean. I don't think I mentioned freezing, I guess, but going from liquid to solid is freezing. Okay. Think about the screen. Sometimes the screen is frozen when I'm teaching, right? I freeze the screen so I can do other things while you guys, look at the notes on the board. When the screen is frozen, it means that it's not moving, right? So think about going to solid. The particles very rigid, stationary, not moving very much. Okay. Screen is frozen. Okay. Finally, KMT explains dissolving and density. Two last things we'll cover in this lesson. When a substance dissolves, now this isn't a chemical change, this is a physical change. Basically, the particles break off from the solid, okay? Little particles break off and they become surrounded by the liquid, okay? So if you have a solid, let's say a lump of sugar or something, and it's going to eventually dissolve because little particles are going to be enveloped by the liquid water around them. And these little particles are going to spread out so much that you can't see them anymore. They're so small, and they're going to dissolve and go to all the far reaches of the solution here. And then all of a sudden it's going to look like they're gone. But instead of being all together here, right, in one big clump, they've all spread out. And they're so small you can't really see them anymore. So, if you think about these particles breaking off and becoming completely surrounded by the liquid particles, that's a motion of particles and that sort of thing. Okay, and of course, when you heat something, those particles all move a little bit faster, and so dissolving, it's easier to do. And I should note at this point, here's a little video, a YouTube video. There's lots of YouTube videos on dissolving, and as a matter of fact, I'd really like you to try this on your own to see this in action. Get 2 glasses of water, okay, equal volumes, but one is hot and the other water is cold. And you take a teaspoon, okay, my teaspoon of, let's say, iced tea mix or something, and you dump it in. You do this, the same volume of water, the same amount of iced tea mix into a very hot glass of water, a very cold glass of water, and then you stir it up, stir them both up at the same time. If you do this at the same time, you really see, the difference. But you stir them up at the same time, and then you watch how each of these samples of iced tea mix, how they dissolve in there. And you'll really see the effect of temperature. Okay? So this would be a good homework assignment for you to watch and observe this. Okay? 2 identical volume glasses of water, one hot, one cold, to see what happens. And finally, when a substance heats up, the particles move more. As they move more, they take up more room. Consider you. If you, okay, were jam-packed right next to, all your classmates, and you occupied this much space, and you were like all holding hands or something, whatever, and you're pretty tight, okay? If I said, okay, you guys need to jump around and move more, even if you're still holding hands, you're jumping around, yay, right? Then what happens is you guys are all taking up more space, right? Yeah, okay. Not very good, you are sometimes. But you see this? More space, because you're moving more, right? And so if that's the case, then this speaks to density. All right? Since density is mass per unit volume, an increase in volume, that is the denominator here, gets larger, and density decreases. All right? So even look at this situation. We have this amount of mass, 1, 2, 3 people, in this space, volume. We have the same mass in a larger space. This is less dense. Okay? Less dense. Okay? So generally, that's how kinetic molecular theory explains density as well. Okay? So that's that lesson on kinetic molecular theory, the introduction to Chapter 8, KMT. And we talked about models and particles, talked about changes of state, gas, liquid, solid, and yeah, that's our lesson for today. And so we'll continue that as we move on. But yeah, watch this video, do this little home experiment, see the effects of temperature on dissolving, and we're going to talk in Chemistry 30 about factors that affect reaction rates. Of course, temperature is one of the chemical reactions affecting those rates. All right, there you go. That's your lesson for today.